the last part of today's lectures, we'll talk now about coordinate systems in the sky and the way we account for time. This won't take very long. We need to have some kind of coordinates. So what astronomers have done is they projected Earth's coordinate systems onto the sky. And as Earth rotates, so would the sky, right? And so when you anchor it not to a point above the Earth, but a certain part in the celestial sphere, then you have celestial equivalent of equatorial system, and that's what it's called. Now, Earth's equator projects the celestial equator, so that's an easy way to account for latitude or declination, as astronomers call it. And you have a choice where to start accounting for the other coordinate equivalent of longitude, which we call right ascension. And the choice was made that this will be a position of sun at the moment of the spring equinox. Now, since you're at Caltech, you all know what causes seasons. The Earth's axis is tilted relative to the plane of ecliptic, and what the equinoxes or solstices mean, right? Yes? Okay, good. Likewise, you know how sun moves on the sphere because the tilt of the axis, it's not always around the ecliptic, but it goes above and below. It's not always on the equator. It goes above and below. It's always on the ecliptic. And so it inspires this kind of sinusoidal motion throughout the year. Summer solstice is what's the highest, and winter is the opposite. Equinox is when it's exactly when equator and ecliptic cross each other. There is a simpler coordinate system, which is for every given point, which is elevation angle, or distance from the zenith, and direction relative to the south. It's alt-azimuth system. That's relevant for telescopes, and so there are proper trig formulae to convert from one to the other. I have to mention two others, which are ecliptic and galactic. Just like we projected terrestrial equator to the sky, and that became celestial equator, defined equatorial system, you can take the plane of the ecliptic, project it on the sky, that defines ecliptic equator, or you can take plane of the Milky Way, and that defines galactic equator. And that actually can see on the sky. Here is the picture of the sky in mid to far infrared in galactic coordinates. So the horizontal reddish streak is the plane of the Milky Way, marked by hot dust. And the fuzzy blue thing is actually another great circle tilted relative to the galactic plane, and that's the ecliptic. Anybody cares to guess why is it fuzzy? I mean, why is it there to begin with, if ecliptic is simply just plane of Earth's orbit?
Is that the result of dust in the
That's correct. It is the result of dust that's been heated by sunlight and emits in infrared. And because dust is a little fluffier than just planetary orbits, so does this. Couple other concepts, and then we'll be done. So we account for time through the Earth's rotation, and so you can count day from, say, noon to noon, midnight to midnight, so it's defined relative to the sun. But during the year, Earth makes one extra turn because it went around the sun. And so relative to the stars, there is one more day in a year. So those are two different time systems. There is synodic, relative to sun, that's what you usually think of as time. And there is sidereal, which has one extra day per year. And that one is relevant for astronomical observations because who cares how Earth turns? It's what happens on the celestial sphere. Now, universal time, or Greenwich Mean Time, or Zulu time, is local synodic time defined through the Greenwich meridian. Right? We are now 7 hours behind it, 8 when it's not daylight saving time. Every once in a while, there is a need to tweak it up because Earth's rotation slows down. And it slows down because of tidal interaction with the moon. And so that's where they add leap seconds. That's where they come from. Two last things. First of all, the tilt of Earth's axis is not always constant. It kind of tends to wobble around. And the period of that wobble is 26,000 years. So Polaris is polar star now, but at some point Vega will be a polar star. And so you have to always define which equatorial system do you mean. Today, in year 2000, year 1950? And so they're all sharply defined coordinate systems astronomers refer to. Axis also wobbles and jiggers, and those are much smaller effects, but still they can be measured. One interesting consequences of this instability of Earth's tilt and orbit is that it leads to the ice ages. This was first proposed by astronomer named Milankovitch, and he figured out how the shape of Earth's orbit might change in time due to the perturbations by Jupiter and instability of this angular momentum vector and so on. And so it's precession and eccentricity and so on, and when you can match that to the fossil record of ice ages, it matches very well. So major climate cycles on planet Earth are due to this dynamical interaction of Earth's rotation with its rotation around the sun and some perturbation by other planets.